Today we'll be looking at some more review for the Unit 2 test in order to try to bring our grades up on the test. So today's objective is I can raise my score on the Unit 2 test if I got less than 100%. And let's do a little bit of review. First, discrete versus continuous. We did this at the beginning of the unit, so it might not be fresh in your memory, but let's do a quick review of what those things mean. So when we're talking about a discrete function, there are several ways you might think of it. You might think of it as separate dots on a graph. So if we had a graph, it might look like dots. You might also think of this as something that is countable rather than measurable, or things happening in chunks, like maybe you get a payment every so often. That would be something happening in a chunk. Or you might think of it as something that cannot be divided infinitely. So if it doesn't make sense to divide it in half or in fourths or in hundredths, then it is not continuous. It must be discrete. Now, to contrast that, continuous functions will have a connected line or curve. They tend to be measurable rather than countable. Rather than things happening in chunks, things will happen steadily over time. And they can be infinitely divided. So if you should be able to divide it in half, or in quarters, or in thousandths, or in millionths. So let's take a look at an example here. Is this function discrete or continuous? Ocean levels are rising about 3.2 millimeters per year. How might we think about this? Well, we can ask ourselves a few questions that should tell us whether this is discrete or continuous. So the first thing we'll ask is what two things are we measuring? Now, when we're talking about functions like this, there are things that we put on a graph, right? Something like this. We have an x-axis and a y-axis. These axes represent something in our function. And so that's what this question is asking. What is this x representing, and what is the y value representing? What two things are we measuring? So in this one, we have ocean levels are rising about 3.2 millimeters per year. This per, or you might see it say each or something like that, that is an indication that our measurements, our two measurements are on each side of that per. One is over here and one is over here. So 3.2 millimeters, that's measuring ocean levels. That's one of the things we're measuring. Ocean levels, and that's going to be in millimeters. And the second thing we're measuring is years. So again, those are the two things that are on each side of the per, or you might see this as each. So the first question, well actually the second question, after we determine what two things we're measuring, is can we divide our first thing in half? Ocean levels in millimeters. Is there such thing as half a millimeter ocean level rise? There sure is. Yeah, there's such thing as half a millimeter. You could measure it. It's very small, but you could definitely measure it. Same thing with a quarter of a millimeter. You could divide a millimeter into 1,000th. You could keep dividing a millimeter smaller and smaller and smaller. That makes this continuous. That makes the first one continuous, so we say yes, this is continuous. How about years? Are years divisible in halves or quarters? Yeah, sure, we can have half a year. We can have a quarter of a year. We can have 100th of a year. We could even have 1,000th of a year. It'd be less than a day. But we can divide time infinitely as well. So we can divide both lengths and time infinitely. If we have two yeses here, then we say this is continuous or continuous, you can think of it as. If we don't have two yeses, so if we have one yes or we have both no's, then it's going to be discrete. So two yeses, continue yes, anything else is going to be discrete. Let's look at some examples of this. Are these functions discrete or continuous? A store receives a shipment of 100 apples each day. There's our each word. So 100 apples is going to be our first one, and days is going to be our second one. So apples and days. And then we ask, does it make sense to divide an apple in half? Can you ship half an apple and deliver it to a grocery store and have it make sense? No. They're gonna reject half an apple. And a quarter of an apple, definitely not okay. And a thousandth of an apple, that really stops being an apple, right? So we cannot divide apples infinitely. We can divide days infinitely. You can have half a day, quarter of a day, a thousandth of a day. All of those make sense. Time is infinitely divisible. But let's see, we have one no and one yes. Well, this is two yeses, so no, it's not continuous. It must be discrete. This one is discrete. Okay, a child gains 4.5 pounds per year on average. There's our word per. So this is going to be our first and our second. 4.5 pounds is the weight of the child. And years is going to be the second thing we're measuring, years. Can we divide pounds in half? Can you have half a pound of something? Sure. You can have half a pound. How about a quarter of a pound? Yeah, you can divide pounds up as much as you want. You could have a thousandth of a pound. So yes, this is infinitely divisible. How about years? Can you have half a year? Can you have a quarter of a year? Yeah, well, we already talked about time. Time is infinitely divisible. Years, days, it doesn't matter. These are always infinitely divisible. So we have yes and yes. Both of these are divisible. Two yeses means continuous. Continuous. For this one. Next one, a broken sprinkler head leaks about 15 gallons of water each minute. What two things are we measuring? There's our each word. So on one side, we have gallons of water. Other side, we have minutes. Those are the two things we're measuring, water and minutes. Can you have half a gallon of water? Sure you can. Can you have a quarter of a gallon of water? Yeah, definitely. Amounts of water, volumes of water are infinitely divisible. So this is a yes. You can have a thousandth of a gallon of water. That still makes sense. How about minutes? Well, we've already said time is infinitely divisible. Whether you're measuring in minutes or years or days, time is always a yes. So we have two yeses. That means this is going to be continuous. Continuous. And last one here. A salesperson gets paid a commission of $400 for each sale they make. There's our each word. $400 is our first thing. Sales are going to be our second thing. So this is money, dollars. And sales is our second measurement. Okay, can you have half a dollar? Sure, that's 50 cents. Can you have a quarter of a dollar? Yes, that is a quarter, 25 cents. Can you have a 100th of a dollar? Yeah, that's a penny. How about a thousandth of a dollar, though? What is a thousandth of a dollar? We actually can't keep dividing money up infinitely. It isn't continuous forever. It just ends at pennies, and we can't get any smaller than that. Then we start rounding. So money is going to be not infinitely divisible, because as soon as we get to 1,000 or 1,000,000, it doesn't make sense to divide it anymore. We can only divide it into hundreds. How about sales? Can you make half a sale? What would that look like? So it's sort of like signing just your first name on the contract and then like only half of it. No. There's no such thing as half a sale. There's a full sale or there's no sale. So this is both no's. Definitely not both yeses, so this is going to be a discrete function. All right, so now let's go over some rules of exponents. Get a little bit more practice on these. Once again, here are our rules of exponents. Just in case you still need them for your notes, this is a great one to take a picture of, put in your notes. Remember, this is a lot of information on one slide. You're not expected to use this all at once or understand all of it all at once. That would be an amazing amount to take in. What you need to do on these problems is figure out which rule applies. So you look at the problem and you sort of evaluate it. Say, does this have multiplication in it? And if it does, you look for something that has multiplication. Or maybe that one. Or if it has a negative exponent, well, you go through, maybe you say, oh, well, there's a negative exponent rule. Maybe I'm going to use that. Or a fraction exponent. So you can look through these and try to find the one that's applicable. So here are some examples. These say rewrite as a fractional exponent. Well, we're going to use the fraction exponent rule, which is right here, which is a to the m over n equals n root a to the m. Remember, our root goes in the denominator, and then our exponent stays in the numerator. So our base is 7. Our denominator is going to be 2, and our exponent becomes the numerator, 7 to the 9 halves. In this one, we have the base is 2. 5 becomes the denominator, and 3 remains the numerator as the exponent. Pause the video and try to do this last one on your own. See if you get the same answer. So this one's a little bit trickier because there's no number in the root. We have to know that they mean a square root when they don't put a number there. That is a 2 root. Oh, now we can apply the same rule. We take the base of 4. Our denominator will be the root number, and our numerator will be the exponent, 4 to the 6 over 2. Well, 6 over 2 simplifies, so that becomes 4 to the 3rd. Now you might have thought of this a different way. You might have noticed that square root of 4 is actually evenly rooted, right? Square root of 4 is just 2. So you might have written this as 2 to the 6th. That's actually the same thing as 4 to the 3rd. You believe it? Because we have this rule, the power of a power rule, that looks like this, 2 squared to the 3rd. That would be multiplying the exponents. 2 times 3 is 6. But 2 squared is just 4, so this is the same thing as 4 to the 3rd. Both of these answers are equivalent, 2 to the 6th and 4 to the 3rd. Both of them would be considered correct. All right, how about negative exponents? How do we deal with negative exponents? It says to rewrite with a positive exponent. So let's look at this. We have a to the negative m is the same thing as 1 over a to the m. So it looks like we just took this negative out and then put this whole thing under a fraction. Another way you can think of it is you can take this negative and rotate it around, like rotate it 90 degrees, just rotate it on its side, and it becomes the one on top of the fraction. So you see how it comes and ends up as the 1. So let's look at these. 3 to the negative 5th. We're going to take the negative, make it the 1 on the top, and then we just put everything else on the bottom without the negative. Same thing here, x to the negative 2. We take the negative, rotate it around, it becomes a 1. We put everything else on the bottom, x squared, x to the positive 2. Next one, we take the negative out of the exponent, rotate it around, becomes the 1 on the top. Put everything else in the denominator, 1 over 8 to the t. And our last one, same process, take the negative, rotate it around, we get a 1 on top, and 14 to the 5th on the bottom. So notice that either of these could be a number or a variable. This is a variable in the base, here's a variable in the exponent. They could both be numbers, but we treat them the same way. You can apply the rule regardless of whether it's a number or a variable. All right, how about this rule? Same base multiplication. Rewrite with a single exponent. So when we have the same base and we're multiplying, then we end up adding the exponents. Pause the video and try these first couple, see if you get the same answer I do. Okay, so we have 6 to the 3rd times 6 to the 5th. Since we're multiplying, that means we're going to add the exponents. This is going to be 6 to the 3 plus 5. That will be 6 to the 8. Same thing here. We're multiplying, so we're going to add the exponents. 5 to the 8 plus 4. That will be 5 to the 12th. Oh, we have a negative exponent here. Is that going to change anything? Do we need to do anything different there? Well, not really. We're just going to add a negative instead. We'll take the same base, base is 2. We add the exponents, 14 plus negative 3. 14 plus negative 3 is 11, so this is 2 to the 11th. And this last one, our base is 10. We're going to add the exponents because we're multiplying, so negative 7 plus 4. This equals 10 to the negative 3. So we rewrote all of those with a single exponent by adding the exponents. How about same base division? This is very similar, but now instead of adding, we're going to subtract the exponents. When we divide exponential expressions, we subtract the exponents. Pause the video, give these first couple a try, then restart the video, see if we get the same answer. Okay, so we're going to have 9 as our base here, and we subtract the exponents, 6 minus 4. 6 minus 4 is 2, so this is 9 squared. You also might see this as 81. I guess it said right with single exponent, so it wouldn't be 81, but this may be simplified. If it's something small, you may see it simplified. How about 12 to the 13th over 12 to the 7th? 12 is our base. We're going to subtract the exponents, 13 minus 7. So this is 12 to the 6th. Same idea here. Our base is 4. We will subtract the exponents, 5 minus 8. We get 4 to the negative 3. And for the last one, 7 is our base, and we get 6 minus 15. 6 minus 15 is negative 9, so this will just be 7 to the negative 9. Sometimes we might need to apply multiple steps, but don't let that freak you out. We just need to figure out what those steps are and then apply them one at a time. So here we have our rules listed, and it says rewrite with a single positive exponent. Okay, so here on this first one we have multiplication. What do you think we're going to use? What rule, what exponent rule should we use when we have multiplication with the same base? Well, we have this one over here where we added the exponents. So let's try that. 10 is our base. We're going to add the exponents, negative 8 plus 2. And that's going to give us negative 6, 10 to the negative 6. But here it says we need a positive exponent. We have a negative here. So maybe we need to deal with a negative exponent. Do we have something that does that? Oh, we do. We have a negative exponent rule. That's the one we went over a few slides ago where we rotated the negative around to the 1 and put everything else in the denominator. So we're going to rotate that negative around to a 1, put everything else in the denominator, and that is our answer, 1 over 10 to the 6th. For this second one, we'll try a different rule. Let's see, we have division going on, same base. So maybe we have same base division, where we subtract the exponents. 4 is our base. We're going to subtract the exponents now, numerator minus denominator. 5 minus 8 is negative 3. Oh, and now we have that negative rule again. We need to do the same thing we did before. Rotate the negative around to get 1, put everything else on the bottom of a fraction. Now we have a single positive exponent. And the last one on this page, 8 to the 4th over 8 to the 9th. We're going to use that same subtraction because of the same base division rule. 8 to the 4 minus 9, numerator minus denominator. This will be 8 to the negative 5. We use our negative exponent rule, rotate that negative around to the 1. We get 8 to the 5th on the bottom. What if we just have variables, though? Does that change anything? Can seem a little bit trickier. Let's take a look. So this says to rewrite with a single exponent, and now we just have all variables in the exponents. Well, let's see. This one looks like we have something, an exponential raised to another power. So do we have a rule that looks like that? Oh, we do. Look how similar that looks to this one. Power of a power. So now we're going to multiply those exponents together. That's going to be 2x times y, because power to power we multiply the exponents. And then I'm just going to bring everything else down. I'm going to do one step at a time. So that'll be 2 to the negative z. Now we have the same base and we're multiplying. So that's this rule, right? Same base multiplication. We add those exponents. So I'm going to add this whole term right here, x times y. I'm going to add it to negative z. 2 is still our base. We have x times y plus negative z. And that is a single exponent. It's a complicated exponent, but it's still just a single exponent with a single base. All right, let's try this next one. Let's see, we have some multiplication going on, some division. Let's see what we can do here. So we know that we have the same base, we're multiplying, that means we're going to add the exponents. So we get 5 to the k plus 3m. And then I'm just going to leave everything else the way it was, with a fraction and the 5 to the m on the bottom. Well, now we have the same base and we're dividing. So that's this guy up here, right? We subtract the exponents down. So I'm going to subtract this one from this whole bit. 5 is my base, and I have k plus 3m, that's my numerator exponent. I'm going to subtract the denominator exponent. K plus 3m minus m. Now you may notice that you can actually simplify this one. 3m minus m, that simplifies to just 2m. K plus 2m. So 5 to the k plus 2m is our answer. Again, that's a complicated exponent, but it is still just a single exponent. So you don't actually need numbers. You could just use variables in your exponents. That works as well. And that brings us to today's objective. I can raise my score on the Unit 2 test. So your objective is to go retake the Unit 2 test, try to bring your score up higher than it was before.